maintain a certain value ratio. So you have to properly select the size of the transistor here to achieve certain parasitic capacitance here. Select the size of the bit line properly to achieve certain parasitic capacitance here. There is one difference and design requirement. The second thing is a sense amplifier is required because this circuit by itself can never make a change from 0 to 1 to 1 to 0. Maximum it can change up to delta, and that delta depends on the capacitive ratio. So if you want to have a larger delta to make the life of sense amplifier easier, then we have to play with this capacitance value. So, and as you can see, for upward change at here, it will stop at here. No further upward change can take place here. For downward change, it will stop at here. And then sense amplifier must be activated to take it all the way to 1, all the way to 0. So here sense amplifier's participation. So sense amplifier is part of the operation. It's a required component of the operation. And the third difference is the read operation is destructive. While you are reading 1, you are bringing it down. While you are reading 0, you are bringing it up by charging. But still, since whether it's a required component or optional component, sense amplifier has become a de facto component for any memory code design. So they are taking advantage of that. So they are saving power by not allowing this cell to change more than delta amount. They are utilizing the sense amplifier to produce full stack 1 and 0. And also they are implementing a RAM cell with the circuit complexity of a ROM. ROM has maximum 1 transistor. DRAM, 1T DRAM will have maximum 1 transistor. And any DRAM you encounter in any of our micro device is based on 1 transistor. So in static RAM, it is 6. That's why. So because of the lower number of transistor count, it will have less power consumption, higher density of implementation, as well as lower area consumption, and also lower parasitics, so that leads to higher speed. So now let's move to the third type of semiconductor memory we are talking about. Before we move to that one, is there any questions on 1T DRAM? So these are the 3 types of memory we're talking about. We covered these 2, we covered these 2. Now let's talk about this one. So up until now, all the logic circuits we have talked about up until 1 to 8 lecture. And then up to this slide, all the memory circuits we have talked about up to 1T DRAM cell. These are all made of conventional field effect transistor MOSFET. Conventional field effect transistor MOSFET, right? There is a gate terminal separated by insulation layer and drain and source terminal. Now, non-volatile read-write memory, the third type of memory other than ROM and RAM, is based on a different types of field effect transistor, which is not conventional MOSFET, and that is called floating gate transistor. So non-volatile read-write memory or ROM compared to ROM, let's see what is happening. ROM, read-only memory, it is permanent. Once you design it, all the informations are hardwired, you can never change it. Non-volatile read-write memory, under normal condition, it acts like a ROM. Even if you take off a non-volatile read-write memory out of the system, even if you turn off the computer or microsystem, it will not lose the data. Theoretically, It can hold the data as long as you want, like a ROM. Of course, there will be some distortion and contamination in long term. So under normal circumstances, read-write memory, non-volatile and ROM, they act exactly like the same. But under special condition, you can rewrite that data in non-volatile read-write memory, which is the difference with the ROM. So that is the versatility. So how do we achieve that versatility? Let's look at the working principle. Non-volatile read-write memory will have a programmable or tunable threshold voltage. By having the ability to fine-tune or program its threshold voltage, it can hold certain electronic information indefinitely unless you apply certain additional voltage or charge or excitation to push that threshold voltage back to its default state. So by default, every transistor has a threshold voltage. It's a technology parameter. But in non-volatile read-write memory, we use a special type of transistor for which we can program or tune the threshold voltage and push it to a different value. By doing that, it can store certain information. And it can store it indefinitely as long as you don't change the threshold voltage by applying another voltage. So, the device that can have programmable or tunable threshold voltage is called floating gate transistor. So, non-volatile read-write memory achieves the ability to hold the data indefinitely and, if needed, change the data by applying an external voltage. They achieve that dual ability by using the programmable threshold voltage property of a floating gate transistor. So now we are going to introduce floating gate transistor. But let us now, before we see the historical development of non-volatile read-write memory. You guys probably were not even born when I was a high school student. So we, at that time, first saw microcontroller-based small robotic car. And it was a wonder to us. And our teacher didn't let us touch that robotic car. And he showed us a magic that he would take out that microcontroller out of the board, put it under a box and expose it under ultraviolet ray to erase the program. And then take that microcontroller back to and plug it on an electronic board and apply some ASCII code to reprogram it. And then put that microcontroller back to the robotic car, and then when it turns on, the robotic car earlier was moving leftward, now it was moving rightward. So that was a magic to us. So those were the first version of non-volatile read-write memory used in those early version of microcontroller, where by exposing those microcontroller under ultraviolet ray, you can electronically erase the data stored in that microcontroller. So earlier it was a left turn signal, now it was a right turn signal. That was the big magic to us. So erasable, programmable, read-only memory, an upgraded version of ROM. A ROM holds data permanently. EPROM also used to hold data permanently, but to change that data in those ROM, you have to apply an external ultraviolet ray to electronically alter those data, to change the material property of those nodes, to change it. So it was a very cumbersome tedious, time-consuming process, three-step process. Take it out, erase it, reprogram it, and plug it. During this process, if you make one mistake in typing the data, one bit, then you have to do it again. Just make it the right time, right? So during this process, you can, and those pins were not very sharp. It was very coarse grained pin, and those circuit boards were also very small. Taking it out, plugging it back, and doing again and again. First time I did microcontroller experience in first year of my electrical engineering undergraduate. Our group, we destroyed like 4 or 5 microcontroller simply because we broke the pin. Because we have to take it out, put it in the ultraviolet ray box, and plug it into a PCB board and put it on the motherboard again. During this time, we broke like multiple pins. And then for the correct one, for which we did not broke the pin, we typed at least one binary bit incorrectly. It's a bit sequence we have to type like manually. There are like 50 or 60 bit sequence we had to type manually. And if you miss one, you have to redo everything. So it was very slow, very cumbersome, very inefficient. But still, there was a significant improvement over ROM. Then, they improved the floating gate transistor. And they needed an ultraviolet exposure that they said that, well, ultraviolet exposure doing another thing. It was creating material defect, holes, trenches on the layer of the chip. After 3-4 use, you have to throw that microcontroller because physically the chip was damaged after repeated exposure to ultraviolet ray. So they improved the floating gate transistor technology. They introduced the second generation of floating gate transistor. It's called Floatox. Right? These Floatox led to the second generation of ROM. It's called electrically erasable read-only memory. Now you don't have to expose it under UV ray. You can put it in a circuit board, apply a very high voltage, which is 4 to 5 times higher than operating voltage of the motherboard. So you cannot keep it on the motherboard. You will burn the motherboard. You have to take it out, put it in a separate electrical circuit board, apply a very high electric voltage, 4 times, 5 times, up to 10 times larger than operating voltage of the motherboard, erase all the data, and rewrite the data using a very high voltage, and then put it back on the motherboard to basically reuse it. But still it's one step because you can do it electrically. Only thing you have to remember, that memory block in that microcontroller must be designed with high voltage tolerant transistors and circuit components. And that voltage is significantly higher than the operating voltage of the rest of the chip. But still it's an improvement, and you don't have to take it and put it in an ultraviolet ray box and physically damage it. So removal of one step and removal of ultraviolet ray exposure, it was a significant component. Now then, further improvement of floating gate transistor technology led to the third generation of non-volatile read memory, which became known as flash memory, the most popular and widely used memory gadgets in our current life. What is the improvement? Improvement is you don't have to take this out of the system. It can be plugged into the system. It can be plugged in your cell phone, battery, or camera, or wherever you are using it. And you can use motherboard level voltage amplifier, system level voltage amplifier, buck boost converter, just to amplify the voltage 1 or 2 times. If the microprocessor is 1 volt, this one is probably using 3 volt. Very small voltage, and you can achieve that using that motherboard level buck boost converter and achieve that voltage you can rewrite it at much faster speed without taking it out of the system. So that saves time, that saves this device. You don't have to put it back and forth on PCB board, right? And you don't have to unplug the system. I don't have to open the cover of this cell phone to take the SIM card out and put it back every time I'm trying to rewrite something. So that is a huge improvement, and only then it became very popular. Until then, these two versions were hardly used. And that was based on the third generation of floating gate transistor pioneered by Intel Corporation, and that is called ETOPS. So, 3 generations of read-write memory, non-volatile read memory, EPROM, E2PROM, EEPROM, and this one has a long name, Flash Electable Erasable Programmable Reader. Now the question is, why it is flash? You can erase everything in one instruction. You can erase block by block selectively any way you want. This ability to erase everything in one instruction and populate it with something in one instruction, you can just drag hundreds of files and then put it. As long as capacity is there, you can write it in just one drag or one copy paste instruction. So that ability is called flushing of data in and out. That's why they came up with, although I did not like the analogy, you know why I'm getting into. So they came up with this flash technology. So that has become now this very popular now. Now we are going to look at, we looked at the commercial version of these 3 generations of non-volatile read-write memory, all based on 3 generations of floating gate transistor. First one was known as FAMOS, second one was known as FLOTOPS, third one was known as ETOPS. But so everything about non-volatile read-write memory is about these 3 generations of floating gate transistor. So we are now going to look at their design and operation. So this is the first generation of floating gate transistor, became known as FAMOS. Floating gate avalanche MOSFET. So, if you look at now this construction, we have the normal gate, we have our source, we have the drain. Inside the silicon dioxide layer in between gate and the body of the transistor, there is an embedded additional gate. That gate is called floating gate. Why? Because it is surrounded by silicon dioxide from all sides. So it's an electrical island floating inside insulation. It is not electrically connected here, here, or here. That's why it is called a floating gate, because it electrically disconnected from every possible terminal in the transistor. So the external gate, the original gate body, in between silicon dioxide layer holds an embedded floating gate. So now, because of embedding this floating gate, the silicon dioxide layer between original gate and the body has to be much thicker. Otherwise, you will not have enough space to house that floating gate. The symbol compared to the regular MOSFET is slightly modified. We pushed the gate little bit further and added extra disconnected line. This line is not connected here because it represents the floating gate. Now the question is how this floating gate operates as a memory. Earlier we mentioned that this floating gate transistor has a unique property, that is programmable threshold voltage. That programmable threshold voltage will give it the ability to store information. First of all, from electronic point of view, what is the definition of information? Definition of information is nothing but a level of charge. If the device can hold two different levels of charge under two different circumstances, that means it can hold two different binary information. If we call the higher voltage binary 1, we can call the lower voltage binary 0. One thing you have to remember, binary 1s and 0s do not need to always have to be VDD or ground. It can be ground and minus VDD. If you have a ground voltage and a negative voltage, that negative voltage becomes your binary low, ground voltage becomes your binary high. All you have to do, a relative difference between two levels. Higher one will be binary 1, lower one will be binary 0, high and low. So that programmable threshold voltage will give its ability to hold two different charge levels across its gate and source or drain terminal. Due to the insertion of this floating gate, due to the thickening of silicon dioxide layer, its original threshold voltage will increase. And also, the device's conductance will decrease. Why? Now that original gate from which you have to apply the electrical field to turn on this transistor to establish the channel, you are applying the gate voltage from further. So, to establish the channel, you need to apply now larger gate voltage. So the voltage that is available to you for conduction above threshold voltage, that window is become narrowing. So effective voltage to send current here and ability to form a strong channel will reduce. So the channel conductance will decrease, threshold voltage will increase, thickness of the oxide will increase. So these are the some design parameter changes due to the insertion of this floating gate. But that floating gate gives us the most important property, programmable threshold voltage. Now let us look at the operation and how do we achieve that programmable threshold voltage. Operation of FAMOS. So, at the beginning, when no voltage is applied at any terminal, everything is charge neutral. Zero voltage here, zero voltage here, no voltage here. So first is the programming of the floating gate. We have to apply a very high positive voltage, 20 volt, when operating voltage may be in the range of 1 to 3 volt. At that time it was 3 to 5 volt. At 20 volt voltage, a very high positive voltage will exercise a strong positive pull on negative electron floating around here from source, drain and the body. Because this device is designed for only 1 to 3 volt. Now we are applying a 20 volt voltage, so this electron will experience a very excessively high attraction towards the gate. So an avalanche tunneling of electron will take place. Avalanche means it is an insulation. Electrically, electron cannot travel through an insulation. But this one will exercise so much force on that this electron will physically tunnel through the silicon dioxide layer and travel towards that terminal which is exercising or applying that attraction force. But as electron travels, penetrates through, all the force it gets achieved from here, that physical tunneling will exhaust all the energy it gained from here. But the moment it reaches the floating gate is what? It is a conducting layer. And for electron, it's a compatible environment because electrons can reside in, flow through a conducting layer, but it is not able to regularly flow through a solution layer. The moment electron reaches here, by this time it exhausted all the energy, so it will start traveling to the left and right and start accumulating in this floating gate. If you keep applying this 20 volt voltage for certain time, enough electron will penetrate through this silicon dioxide layer and accumulate on the floating gate. Now, let's say remove that 20 volt. What happens? These electrons are already trapped in this floating gate, producing a negative charge layer in the floating gate with enough electron accumulated. The moment you remove the 20 volt programming voltage, what happens? Those electrons cannot go back to the silicon because nothing is pushing them down. This electron cannot jump from here to here because there is an insulation sitting. This 20 volt force is no longer there. So the result of applying a 20 volt or very high voltage for certain time is the floating gate becomes a negatively charged layer. Right? Now, if I want to activate this device, turn on this device to establish the connection from source to drain, what I have to do? I have to apply a positive voltage, let's say 5 volt, which is operating voltage. First, I have to overcome this negative barrier, neutralize this negative barrier. Let's say it has a 2.5 volt equivalent of negative charge accumulated. So I have to first apply up to 2.5 volt positive voltage to neutralize them, right? Then whatever additional voltage I apply above that, it will be used to establish the channel, right? So because there is already, because this one must have a net positive voltage to form the channel. But in between, as if there is a negative 2.5 volt battery is sitting in the opposite direction of electrical field you are applying. First, you have to have a voltage above 2.5 volt to have an edge. So that what is happening? Your threshold, effective threshold voltage for this device is increased by 2.5 volt. Now, if I don't do anything, if I read the terminal voltage across this transistor, what I will see? I will see a 2.5 volt negative voltage. And if I do not apply any voltage here, after programming it, this one theoretically will hold that negative 2.5 volt indefinitely because it is surrounded by insulator, right? So by programming it certain time with a very high voltage, I have achieved a permanent negative voltage state across this terminal, a negative voltage level, charge level. If I interpret the negative charge level as binary low level, that binary low level can be held indefinite time because it is surrounded by insulation unless I do anything. Now if I want to neutralize it, change it back to original zero state, what I have to do? Now I have to apply a 5 volt probably will not act. I have to apply a much higher voltage, a negative voltage here. This is for, if I want to operate at a 5 volt, it will see a 2.5 volt negative volt, then anything above will turn it on, and then when I read it, I will see a 2.5 volt negative sitting here. This electron will not go back because nothing is pushing them. This positive 5 volt will keep them in their position because electron will be attracted to positive 5 volt. But it is not large enough to force them to jump from here to here. So they will remain at their state But this terminal and this terminal, when a connection is established, between them they will read a negative 2.5 volt, and I can interpret that state as a binary low state. Now if I want to achieve a binary high state, I have to neutralize this 2.5 volt. What I have to do? I have to take it back to the programming state. Then now I have to apply a negative 20 volt. What negative 20 volt will do? Now this negative 20 volt will apply a very strong repulsive force, because negative will repulse negative. So the electron now, it was getting an attraction upward, now they will be repulsed downward. So now, same amount of force will push them back. So this electron now will have another avalanche tunneling, physically penetrate to the silicon dioxide layer and come back to its body. And if you keep applying this negative 20 volt for long enough, all the electron will push back and it will become neutral. Floating gate total accumulated charge will become 0. Now I apply that 5 volt operating voltage again. It doesn't need to overcome this negative 2.5 volt. The regular threshold voltage will apply, and after the threshold voltage, it will be on. If I read the voltage across the terminal, it will read a 0 voltage here. Earlier, it read a negative 2.5 volt, now it will read a 0 volt. So that is a higher state compared to the earlier state, so that is binary high. So by programming its effective threshold voltage, effective turn on and off voltage, by accumulating or emptying this floating gate, I have the ability to achieve 2 different threshold voltage and achieve 2 different voltage state across the terminal of this transistor, and 2 different voltage state can be interpreted as 2 different binary information. High is 1, low is 0. So that is the basic. So what is the problem with this floating gate transistor? The problem with this floating gate transistor is first requirement of very high voltage. These devices are designed for low voltage. When you apply such a high voltage, physically voltage get damaged, and also penetration of electron damages the insulation property here. After several use, some electron may not be able to reach all the way to the floating gate and come back to the body. They will be trapped inside the silicon dioxide layer. So over the time, that silicon dioxide layer will have many electrons trapped, so it will lose its insulation property and the device will cease to operate or it will malfunction. So the reliability of this device after few operating cycle, because of the excessive voltage, and inadvertently, if you do not separate rest of the circuitry from this memory device, you may burn the motherboard or the rest of the microprocessor because of this excessive voltage. And it is not very efficient to penetrate electron through this entire length of silicon dioxide. But the problem is, at that time, IC processing was not smart enough to lower the thickness of the silicon dioxide. So what is the solution? Solution is, if I can bring this floating gate transistor closer to the body, if this silicon dioxide layer is narrower, I need lower voltage to instigate the avalanche, lower voltage to push them back. So operating voltage will go down. I can keep it on the chip. Here I have to take it out of the chip because this voltage is too high for the chip to tolerate. So then they started looking for ways to decrease the operating voltage to write and erase this voltage level. And the solution is, bring this one closer to the body, reduce the thickness of this silicon dioxide layer. So initially, they were not able to reduce the thickness of the silicon dioxide from end to end. They came up with a solution that is the second generation of floating gate transistor flow tops. What they did, well, why don't we try to bring a small portion of floating gate closer to the body and the source drain. That's what, make a small trans, so this portion of the body becomes closed, the thickness of silicon dioxide here is much reduced. So when I apply a positive voltage here, at much less voltage, some electron will be able to tunnel through this thinner layer of silicon dioxide and accumulate here and produce a negative charge layer here. Similarly, when I apply the erasing voltage in the opposite direction, at much lower magnitude negative voltage will be able to repel the electron and push them back to this. So I'm creating a narrow window and door to pull them up and push them back at much lower voltage. And at that time, the thickness, they were able to bring it down to 10 nanometer. Rest of the area probably 20, 30, 40 nanometer thickness. So there is one improvement. That's how they were able to program and reprogram it, keeping the chip on the motherboard, so that they can generate the voltage, they can do that electrically. They don't have to do ultraviolet ray, and that increase the reliability. So you can do more and more operation, and it increased its reliability up to 10 to the power 5 erase and write cycle. About what? 100,000 times you can do reset the time. Like this was like few hundred times. But it still that is in a day-to-day, when we are using this, you have no idea how many millions of times we are exchanging bits. So you don't actually even 100,000 erase and write cycle from this was not enough. So they started looking for further improvement. And finally, Intel microprocessor, their processing system, they came up with smart processing to bring down this thickness in the range of 2 to 5 nanometer. Entire floating gate brought down very close. So the problem with this one is only a narrow window is available for pushing up and down the electrons at lower voltage. This entire portion is not participating in programming and erasing because it needs very high voltage to create tunneling here, right? So, as if you have a very large building, only a small narrow door. So the speed of operation was not at the expected level required by current microprocessing system. So, the third generation of floating gate transistor was introduced, where they were able to reduce the thickness of this silicon dioxide down to 2 to 5 nanometer. So the entire floating gate can be placed very close to the body. Now with only 2 to 3 times higher voltage, which can be generated by motherboard with its inherent converter on the motherboard. Now you can do programming and erasing at much lower voltage. Typically, this flash drive, they work in the 3 to 5 volt range. And motherboard microprocessor, and there is 1 volt. So same operation. The only thing is that since the programming erasing can be done at lower voltage due to the presence of very thin, ultra thin silicon dioxide layer here, we can do it at much higher speed because now tunneling will take place to the entire surface, not through only the narrow window. So that actually led us to the introduction of flash memory. And it brought down, originally it was introduced for 12 volt, now we are talking about in the 3 to 5 volt range, operating for any flash memory you use. So that is the underlying technology for all non-volatile read-write memory or non-volatile ROM, the floating gate transistor, T generation FEMOS, FLOTOPS and ETOPS. So that's the end of the semiconductor memory. Now we are going to talk about some high-level performance and reliability issues that are common to any types of semiconductor memory, whether it's a ROM, RAM, flash, it doesn't matter, whether it's a foreground, background, synchronous, asynchronous, no matter what is the type and application of memory, in any micro and nano system, memory circuits and cores in general have some design requirements, in general have some challenges and issues. And so let's look at those. Two of the most serious design challenge for memory circuits and core are, number one, low signal to noise ratio. Noise is universal. Electrical noise we're talking about, electronic noise. The noise, this is not the noise I'm making. Electrical noise, what is electrical noise? What is noise in electrical electronic sense? It's an unwanted electrical signal injected or imposed on your circuit node, on the desired or wanted electrical signal. Any distortion injected from any source, electrical distortion on the circuit node where you want to hold certain electrical value, that is a noise. In memory circuit, we are not allowing binary signals or any signals to make full voltage swing 0 to 1 and 1 to 0 transition. They are operated at a much reduced voltage swing, 20%, 10%, 30% of VDD. So the signal itself is lower. So now same amount of noise compared to logic circuit can impact a memory circuit much severely than a logic circuit, because logic circuit is working at full strength 1 and 0. So that means inherently the signal to noise ratio inside memory is always low. And signal to noise ratio is a very, very important reliability measure. If it is low, that means a smaller amount of noise can distort or destroy your information. The second most serious impact is, since memory circuit is the most densely packed component inside your IC, that means in every rows and columns, there is no gap. Millions of transistors and circuit components, they're arranged in a very densely packed area inside the microsystem, so that you have the ability to store billions of bits of information, right? That means that any material defect, any structural defect on that microprocessor chip will affect more severely in memory core than the logic core. Why? Logic cores, they are sparsely distributed circuit. So what is this defect we are talking about? The chip is made of a material collected from sand. Nobody can guarantee that material is 100% pure. No matter how many different chemical material processing cycle you go through, there will be always some contamination. And you can never guarantee that even if it is 100% pure, can you guarantee that every single silicon atom will be perfect? Some of them will be physically deformed, thereby producing physical defect, material defect, contamination in the chip you are talking about, the silicon layer. The chip is nothing but a piece of silicon, right? So in that silicon chip, when you have very, very densely packed at picometer, nanometer, fraction of a nanometer distance devices sitting side by side, smallest amount of defect may affect tens of memory cells. But in the logics, they are sparsely located. So any defect may not impact any logic device, right? That's why structural and intermediate defect will be very serious issue in case of memory core. Yes.
I mean, isn't polysilicon by nature filled with defects? Because it's
Yes, any silicon, any material, not only silicon, there is nothing called 100% pure. From environment, what we use, even in the lab creation, there can be contaminant from lab environment. And even if you can create 100% pure silicon, you cannot say that every single atom will be perfectly aligned at its desired crystal position, right? So there will be mechanical defect, structural or material defect. So, and you as the designer, so you have to address these two issues and you have to design so that your design, your memory is robust against these two threats. So, to address the low noise signal to noise ratio problem, what you have to do, you as the designer, you have to make your circuit significantly more robust, tolerant against noise, right? More tolerant than the logic part, control part. Now, to do that, you have to know what are the sources of noise, where the noises are coming from. The sources of noise in a memory core can come through different routes, different source. Word line to beat line coupling. Word line and beat line, they are sitting side by side. When a signal activity is going on in word line, let's say word line is activated going up, at that time you are reading or writing as 0, so beat line is at 0. Word line is going up, beat line is sitting at 0. Across them there is a parasitic capacitance, so it will inject a charge this way or this way. That is called word line to beat line capacitance. And there are thousands of beat line running parallel. You are writing 0 here, 1 here. One is going up, one is going down. Between them, electrostatic coupling will take place. That is called beat line to beat line coupling, right? And then, in memory, when you are basically reading and writing at a very, very high speed, that means these beat lines and word lines, they are switching up and down, up and down. When signal switches at a very high speed, you can never guarantee that they will smoothly go up and smoothly go down. They will create spikes as it goes down and up very high speed, irrespective of whether there is a coupling from neighboring line or not. Like any electrical signal, if it goes up very fast and down, it will create spikes in the signal. That is called switching noise. Further you increase the speed, those spiking noise, the switching noise will increase. So increase switching noise at higher speed. That is the third source of noise. The fourth source of noise, one if you ask this question after last class, radiation. Alpha particle induced soft error. This is a critical problem for memory, particularly any microsystem that is working in high radiation, high temperature environment. And then, fifth one is charge leakage. Any electrical node, no matter how strongly you design it, there will be leakage coming from many different sources. In logic circuit, when it is holding full strength VDD or full strength down signal, small amount of leakage may not be able to distort it that much. But memory circuit is operated at a much below full voltage swing, so small amount of leakage may take it up or down below your expected level, so you may lose that information. So charge leakage is the fifth source of noise and it is very severe. So now the question is, let me elaborate on this one a little bit, although it's an advanced topic. In the environment, there are many, many temporary particles roaming around. Not in hundreds, not in thousands, in billions. And inside the material, there are electrons, protons, and neutrons. And there are many, many temporary material. And any material is emitting those temporary particles into the environment. So our environment carries billions of temporary particles Some of them are neutral, some of them are positively charged, some of them are negatively charged. The amount of charge is very, very minuscule. We or any object cannot detect it under normal circumstances. But in high radiation industrial manufacturing environment or in high temperature environment, the number of particles emitted into the environment will be significantly higher than a normal room temperature, regular this classroom environment. So any unknown particle, commonly known as alpha particle. Some of those alpha particles will carry charge, some of them alpha particles will carry no charge, neutral. So if a memory which is by design is operating at a low voltage level, all of a sudden in a high radiation environment, a bunch of alpha particles, all negatively charged, fall into that node. What will happen? The node voltage will fall down. It is already reduced, a delta amount up or down. So it may inadvertently flip the bit. That inadvertent flipping of single memory bit in memory literature is called soft error, also known as single even upset, SEU. In memory literature, these two are common term. This is the flipping of one bit. It cannot flip many bits. If you have billions of bits, maybe one of the bits will have this rare occurrence of being injected with, from environment, a bunch of alpha particles, all positively charged or negatively charged, thereby flipping 1 out of 1 billion bit. But if you have a 256-bit Windows Word, if one bit is flipped, this entire word information is incorrect, right? Your bus is sending 256 bit at a time. Out of that 250-bit sequence, if one bit is flipped, the entire sequence is sending wrong information. So that is called single event upset. 1 out of 100, thousands of billions of bit is flipped. The word corresponding to that bit will be now erroneous. So that is called alpha particle induced soft error. It is the rarest among all the noise source, but it is more prominent in memory circuit compared to logic circuit. In logic, it cannot make that impact because logic circuits carrying full strength signal. So, because of the yield problem, as we mentioned, because of the defect problem, structural, yes.
Why is there no word line to word line source of noise?
That is also be there, but in general, what I'm trying to say here, that line to line coupling capacitance. So it can be, you can add actually a third coupling capacitance, word line to word line capacitance. If two word lines are side by side, but that one, there is a reason why I did not mention, because you are activating only one word line at a time. Other word line are not activated. So I am not reading those word lines. So that's why I am not bothered. If that word line gets injected in a charge from the word line you are activating, right? So I am not worried because that word line I am not even accessing. I am not reading anything on the word line. So at any given clock cycle, I am activating only one word line at a time. That's why that coupling capacitance is there, but it is not impacting my operation in my current clock cycle because I am not accessing that word line. But on the other hand, a word line horizontally may be running through like thousands of bit line. So every time when I'm activating a word line, I'm also connecting with every bit line in that horizontal direction. That's why I have to care about bit line to bit line capacitance, because while I'm sending 1 here, I'm sending 0 here, I want to make sure that this one or this neighbor is not affecting my 1 or 0. That's why we added bit line to bit line capacitance, but we did not add 190 watt capacitance, but physically that coupling capacitance will be there. So, a good question. So because of this structural defect or intermittent defect or material defect, memory yield will be always less than you designed for. So if you want to beat like 1 billion binary bits in rows and arrays, you have to design, you have to add extra 20%, 30%, because memory yield is always less than what you design. And memory yield is less, why? Because of the material defect, also process variation. What is process variation? Let's say you are designing a memory core, 5 gigabytes memory core with 18 nanometer transistor. So let's say that whole design needs 10 billion transistors. Can you guarantee that every single transistor you are drawing or automated process that is manufacturing it can be exactly 18 and no? 5 to 10% of them will be longer than 18 nanometer, 5 to 10% will be shorter than 10 nanometer. What if it is like too short? At that time probably transistor will not ever be able to give proper operation. So even if there is no material defect, even if there is no physical breakage, intermediate structural defect, but the process through which you are implementing the design will not be able to implement 18 nanometer exactly every time you are printing it. So, and also the thickness of silicon dioxide, the length of the wire, all these dimensions and material composition, we experience variation because of the limitation of the process itself. That's why the yield of the memory process will be always less than what you design. We will start from here. After Thanksgiving, enjoy your break, and I will see you Tuesday after the
By the way, did you get the extra lecture?
I am actually going to record it this weekend and upload it.
Awesome, thank you.
I lost the